This lesson we're going to look at applications of solving linear equations. And we want to be able to set up and solve many problems. And this is a challenge. This is a very challenging section because every problem is a little bit different. And we want to be able to find sort of the common thread on how to set these up. And these are challenging, so don't be discouraged if you don't get it immediately. You sometimes have to read the problem several times to get these. So let's begin. I've got 5 or 6 examples I want to show you. Okay, Lex is twice as far from the finish line as he is from the start of an 18-mile race. How far has he run? So how do we begin setting these up? So step 1 is you have to read the problem. If you don't understand it, read it again. You have to read the problem 3 or 4 times. Identify any given information. Sometimes this means we have to draw a picture of something. And then you begin to label the drawing if the drawing is appropriate. If you don't have a drawing, you begin to sort of figure out how the different pieces relate to each other. Maybe there's a formula involved. Maybe just some sort of common sense can help you to connect these thoughts. And then you solve it. And at the end, once you solve it, don't move on. Make sure this answer makes sense. So if you're talking about finding the length of a side of a rectangle and you end up with a negative number, that doesn't make much sense, right? So make sure your answer sort of makes sense in light of the given information. So let's go back to this problem here. So what's one thing you could do to kind of help yourself out, help you be able to visualize what's going on here? Good, let's draw a quick picture. So we've got start and finish, and then we've got little Lex in here. And I kind of draw, you don't have to be perfect on these drawings. He's twice as far from the finish line as he is from the start. So I put him a little bit closer to the start than the finish line. That way in the end, when I get my final answer, I can kind of look at it. You can't always do that with these. Sometimes the shapes are just too complicated and you can't foresee how big angles are going to be and stuff like that. But this one I could kind of see. So how far has he run? Now what do we do? So let's start labeling some stuff. So he's twice as far from the finish line as he is from the start. So do we know his distance from the start, from here to here? We have no idea what that is, right? So we'll call that unknown x, some distance x. So what's our distance from Lex to the finish line? Well, suppose if this were 4, let me just make that number up. If that's 4, how far is he to the finish line? Well, he's twice as far as he is from the start. So that'd be 2 times 4. So whatever that number is, it's 2 times that. So this is going to be 2x. That's this distance here. Okay, next, what else do we have? It says that the race is 18 miles long. So we know this distance here, the total distance, is 18. So now we have a pretty good visual of what's happening here. Now you probably could have played with some of the numbers here, but if I had made this a 19-mile race, that makes it a little more challenging. But I want to do one with the math. The math didn't kind of get in the way of setting this one up algebraically. So how do these 3 pieces connect? Well, his distance from the start plus his distance from the finish should equal 18, right? So we can just set that up as an equation. X plus 2x needs to equal 18. And then we solve for x. And this one's relatively easy to solve. 1x plus 2x is 3x. And then divide through by 3, and we get x equals 6. So after you get this, make sure we've actually answered the question. So does 6 answer the question? So how far is he from the start of the race? How far has he run? That does answer the question if I put some units on here. So he's run 6 miles. So this is distance here, 6. It didn't ask this, but how far does he have left to run? Good, 12. And you could have gotten this in one of 2 ways. You could have said 2 times 6, or you could have done 18 minus 6. Either one gives you exactly the same answer. So our answer here was 6 miles. Example 2, a 480-meter wire is cut into 3 pieces. The second piece is 3 times as long as the first. Third piece is 4 times as long as the second. How long is each piece? I really want you to pause the video here, give yourself some credit, and try to get problems set up. Welcome back. All right, so we've got to draw a wire here, and we'll break it into 3 pieces. The first piece is the smallest piece, the second piece is the next largest, and the third piece is the biggest. So I drew it that way. You don't have to. We basically just need to split this up into 3 different pieces. And then let's label this. The second piece is 3 times as the first, third piece is 4 times the second, so we don't know anything about this first piece. So that's what I'm going to call x. So if that's x, the second piece, here's piece 1, here's piece 2, and here's piece 3. How long is this second piece? It says it's 3 times as long as the first. So this piece is 3x. And what about the third piece? It's 4 times as long as the second. So 4 times as long as, it's going to be 4x? No, that would be 4 times as long as the first. It's actually 4 times 3x. And let's simplify that as 12x. It'll just come out a little bit easier algebraically when we set this up. And what else do we know? The total, right? The whole piece is 480 meters long. So I think we've got something now. We know that when we add up piece 1 plus piece 2 plus piece 3, we better get 480 meters. So piece 1 is represented by x, piece 2 by 3x, and then piece 3 is 12x. And this needs to be 480. And we just use our equation solving ability we've acquired in earlier lessons to solve this. So 1x plus 3x is 4x, plus 12x is 16x, equals 480. I'll divide both sides by 16. And I'll get x equals 30. So piece 1 is 30. So let's label this piece 1, piece 2, and piece 3. So piece 1 is 30, and let's put some units on here, 30 meters. How about piece 2? Piece 2 is 3 times piece 1. So 3 times piece 1 would be 90 meters. Now piece 3 is 4 times piece 2. So what's 4 times 90? 360. You can use a calculator if you need to. But 4 times 9 is 36, and bring down your 0. 36. Okay, and always look back to make sure this sort of fulfills the problem. A wire's cut into 3 pieces, so we have 3 pieces here. The second piece is 3 times the first, so the second piece, 90, is 3 times 30. The third piece is 4 times the second, and 4 times 90 is 360, or 12 times the first piece. 12 times 30 is 360. Okay, example 3. Top of John Hancock building is a rectangle whose length is 50 feet more than the width. And it gives us the perimeter of 520. Find the length and the width of the rectangle. And then find the area of the rectangle. So here's kind of like a part A, and here's our part B. Pause the video here, see if you can get it set up. Okay, welcome back. When you're solving this one, hopefully you all drew a nice rectangle. So where's our rectangle? Now let's begin to label it. So we've got a rectangle whose length is 50 feet more than the width. So there's the width. The length is that side, but we can go ahead and translate that into 50 feet more than the width, which is W plus 50. What else do we know? We're given the perimeter is 520. We'll let P be the perimeter. So we have to have some relationship between the length and the width and the perimeter. Well, we've got one, right? The perimeter is twice the length plus twice the width. And I also need to know the area. I'll go ahead and write that formula down. A equals length times width. So let's first find the length and the width of this rectangle. What are we going to do? Well, we're going to plug everything in. We have 520. So this is all the given information. I really haven't calculated anything, but it's good to write that down. I can take this 520 and substitute it in for P. I can take this W plus 50 and substitute it in for L. L is W plus 50, so I'm going to replace L with W plus 50. Because we need this is one equation with one unknown. So your second line would look something like this, or exactly like this. 520, we substitute that in for P, equals 2L, this was L, plus 2W. Okay, now we need to solve for W. We can use our newly found equation solving skills, and let's go ahead and solve that for W. So we're going to distribute the 2 through. So we get 2W, 520 equals 2W plus 100 plus 2W. I clear the parentheses. Let's combine our 2W's. We'll get 4W plus 100. Now we're going to subtract 100 from both sides. I'm eliminating all those little steps. We can do that in our head, I hope. Well, 520 minus 100 is 420. Last step, divide by 4. We get W is 105. So if the width is 105, what is the length? Well, we know we have a formula here that relates the length and the width. I'm just going to plug my W of 105 in for the length. The length is 50 feet more than that. So the length is 155. So this is the first part of the problem. This answers part A. How do I find part B? Well, I'm given the length and the width. Now I can use my formula of the area. We'll bring it down here. There's length times width. Plug in the length and the width. And we get 16,275 feet squared. Really, I should have put units on here. So feet and feet. And it's up to you if you use units when you're calculating or if you just know at the very end to put them in. Example 4. Donetta paid $52.35 for a coat that was on sale for 30% off. What was the original price of the coat? Okay, so rather than heading straight to the algebra for this one, let's just use our noggin and see if we can sort of model what that algebra would be. So we know that the coat, the sale price is $52.35. What was the original price of the coat? It has to be something more than $52.35, right? And so let's just suppose that the coat, here's the mathematical symbol for suppose that the coat's original price, we'll let P be the original price. Let's just suppose it was 60. It probably wasn't, I just made that number up. How would we find the sale price? We would take 60 and we would subtract, it's 30% off of 60, right? So we would subtract 0.3 times 60. And that would give me the sale price, whatever that happens to be. Okay, we'd say 60 minus 30% of 60. Well, I just made this number up, right? You could do this with a bunch of them. You could kind of guess and check. You could pick 60. If that doesn't work, pick a number a little bigger than that, pick a number a little smaller until you hone in on it. But rather than doing that, instead of using 60, I'm going to use a variable. You could use X, but let's use P. Actually stands for price here, original sale price. So we'll have P minus 0.3P equals, and we know what the sale price is, $52.35. And we'll leave the dollar signs off for now. Now we're going to solve for P. So this is understood 1P. So 1P minus 0.3P is 0.7P equals 52.35. Last step, we don't freak out if we see a decimal. We just do our operation, divide both sides by 0.7. Then get your calculator out. And so we'll do 52.35 divided by 0.7. We get 74.79. That's in dollars. We won't forget the units. So that's the original sale price was $74.79. You can check this out. I mean, it would have taken us a while. Started with 60. That would have been too low. I would have bumped it up to 70. That would have been too low. Maybe 80. That would have been too high. Come back to 75, and I would eventually have found it. But this is significantly easier, right? No, some of you are saying, I can hear you right now. These do take some practice. So let's check this out. If it were 74.79, now we may be off maybe by a penny, but do some rounding. 74.79 minus 30% off of that 74.79, and we should get very close to 52.35. Well, look at that, 52.35. So we're pretty confident that our answer is correct. Okay, Elmer Dinkley paid $105 for his math book, which included a 9.5% tax. What was the price of the book itself? So pause the video here, see if you can work with this one. Do it very similar to how we did the last one. It's slightly different though. So make up a number that it could possibly be, and see if you can figure out how would you add the sales tax to it. So make up some value that could be the original price of the book itself. And then create some sort of equation with that, and then see if you can go ahead and solve it. All right, welcome back. So what'd you do? The way I usually start these, I'm not good at going straight to an equation on these, particularly in the beginning. Now once I do a problem 100 times, I can do it. But until then, I have to kind of make up some numbers in order to wrap my brain around it. So the original price is certainly going to be a little bit less than 105, right? If this price includes the sales tax, what was the original price of the book? So let's say it was $90. So let's just suppose the price were $90. How would I add sales tax to it? Well, I would say 90 plus 0.095, right? 9.5% to convert percent to decimal. We shift the decimal place over 2 places, times 90. And that would give me the total price, whatever that happens to be. I mean, I can try it now. So we could say plus 0.095 times 90. And we get 98.55. So if I were to guess a man, I have to go a little bit higher than that, right? Maybe it's $95. So 95 times, plus, I keep saying that, plus 0.095 times 95. I'm getting closer, so something a little bit more than 95. I don't really feel like guessing too much more on that. Let's set this up. So this is a number I just made up, that 90. So I'm going to replace that 90 with my variable. Let's use p again. So p plus 0.095p equals, and we know what it's equal to. It's equal to $105. I'll leave the units out for now. And solve this equation. So 1p plus 0.095p is 1.095p equals 105, and then divide both sides by 1.095. So our mechanics are exactly the same when we didn't have decimals. The calculator does not freak out like we do when it sees decimals. 105 divided by 1.095. And we get 95.89. So let's come back up here. So the original price of the book was $95.89, and that kind of jives what we did when we picked some number. If we knew it was going to be something a little bit more than 95, I probably would have gone to 96. That would have been too much, then gone back down, and I could have played around with it until I got it. Let me put my $sign in there. There we go. Okay, last example. The second angle of a triangle is 4 times as large as the first, and the third angle is 5 degrees more than the sum of the other 2 angles. Find the measure of the second angle. So, pause the video here. See if you can play around with this. It'll mean a lot more to you when you do that. And if you miss it, that's okay. Rather than just watching me do a problem. See if you can do a couple of these on your own. All right, welcome back. When I'm in class giving problems like this, I see students looking at it and staring at that problem for 2 or 3 minutes, which is, at least they're not giving up. But what's one thing you could do to help get your mind around this problem? Good. Draw a picture. Every one of you should have a picture of a triangle drawn. So there's our triangle. Let's label the picture. So angle 1, angle 2, angle 3. And don't spend a lot of time, on how you labeled it. You could have drawn the triangle any way you wanted. You could have done it like that. It's fine. Sometimes the triangle ones are a little harder to tell. It looks like the first angle is the smallest one, and then the second angle is the next, and then the third angle is the largest. That's sometimes kind of hard to do. It's not that big a deal in the end. Okay, so how do these relate? The second angle is 4 times as large as the first. So we know nothing about the first angle, so that's going to be my x. The second angle is 4 times that, so it's 4x. The third angle is 5 more than the sum of the other 2. So the sum means add, right? So I'm going to add x plus 4x plus 5. That's going to be the third angle. Let me pause there for a moment. Make sure you understand that. So it's the sum of the other two plus 5 degrees. It's 5 degrees more than the sum of the other two. Now I can combine that, right, x plus 4x, and get myself 5x plus 5. Looks a little bit easier on the eye there. Now, what do we know about this? What do we know about angles 1, 2, and 3? We know that the sum of those angles, or maybe you don't know this, the sum of these angles is equal to 180, left on my degree symbol there, 180 degrees. So angle 1 plus angle 2 plus angle 3 is 180. So now we're just going to fill in. This here is the hardest part of these problems, is kind of getting it set up and getting it diagrammed and labeling and figuring out how all those pieces connect. Generally, the solving is the easiest part. So now what are we going to do? So if you've gotten this far, go ahead and pause it here and see if you can solve this equation. Okay, how do we do? So angle 1 is x, angle 2 is the 4x, and angle 3 was the 5x plus 5. This one right here went with angle 3. 4x went with angle 2, and the x went with angle 1. Combine some like terms, you get 10x plus 5 equals 180. 1x plus 4x is 5x plus 5x is 10x. Subtract 5 from both sides, you get 10x equals 175, and then divide by 10, you get x equals 17.5. Have we answered the question? And technically this is x is 117.5, so angle 1 is 17.5 degrees. But we don't want angle 1. I mean, we needed angle 1 to get angle 2, most likely. So what do I have here? Find the measure of the second angle. So the second angle is angle 2, which is 4x. So angle 2 is equal to 4x, so we say 4 times 17.5. And we get 70. Now there are a couple of clever ways you could have done this early on. We could have solved for 4x here. I would have given it to you. That's a little harder for students to see sometimes. So I usually go ahead and solve for the x, and then I go back and look to see what I need to plug it into and plug it in. So 70 degrees is the measure of the second angle. You can go ahead and find the measure of the third angle by plugging 17.5 in for x if you wanted to. It didn't ask for that, so I'll leave that as an exercise for you. These problems are challenging. This is one of the more challenging topics that we cover in this course, so these take some time. We'll look at these more in class on the following day.